let's do the digital logic test question from Thursday. We're asked in part A to give the truth table for a NOR gate. So let's name the inputs X and Y as it does in the question and tabulate all possible inputs and then figure out what are the outputs. Now, NOR is short for negated OR, so if we figure out what OR would do, NOR should do the opposite. 0 or 0 is 0, so NOR will give us 1. 0 or 1 is 1, so NOR will give 0. 1 or 0 is 1, so again NOR gives 0, and 1 or 1 is 1, so again NOR gives 0. That's hopefully just lecture note material, but we're going to be using NOR gates to do some construction in the rest of the question. Okay, let's move on to the next part of the question, which relates to a 7-cell display, which were quite common in early digital watches, and you can still get them to plug into things like an Arduino or a Raspberry Pi. And what they're used for usually is displaying numbers by lighting up segments of light emitting diodes. So here I've called the 7 segments A, B, C, D, E, F and G on the bottom, and I've given you the display patterns for the numbers 0, 1, 2 and 3. And our task is to take a 2-bit signal representing a number in the range 0 to 3 as a binary number and explain how to control each segment of the display so that when we send in the binary signal for 0, the display shows 0 and so on. So what we have to do is build a bunch of circuits, one for each of the cells, to control it from the signal that gives the numerical input. So that's to say, and here I'm going to need 2 boards at once. You're going to have to zoom out. We are going to need to build a bunch of circuits which take the 2's and the 1's of a 2-bit binary number and gives us, so that's going to be all possibilities, 0, 0, 0, 1, 1, 0, and 1, 1. And they really represent 0, 1, 2, and 3. Then we have to explain which bit patterns are going to come out. So what the question is really asking us to do is to transcribe this diagram into a truth table, saying what each of these individual cells have to do when we're trying to display each number in turn. So let's work through them. For 0, we have A, B, and C, and we have E, F, and G. But D is not lit up to display a 0. For 1, only C and F are being displayed, and we have nothing everywhere else. For 2, we have A, C, D, E, and G. A, C, D, E, and G, and zeros for the other 2. And finally, for 3, we have A, not B, but we have C, we have D, we don't have E, we have F, and we have G. So that is the solution to part B. we have figured out what signals we need to send to each of the to the cells in order to display each number. Our next task is then to build circuits to control A, B, C, D, E, F, and G, given the inputs 2s and 1s. That's to say, as ever with the truth table, we have the inputs on the left and the outputs on the right. And we're going to need to build these from NOR gates. So before we even get started building circuits from NOR gates, we should get ourselves better equipment. Let's begin by defining NOT, OR, and using NOR gates. We can define NOT by tying NOR's legs together. You can see from the truth table that if you send 2 zeros in, you get 1, and if you send 2 1s in, you get 0. So that will behave like a NOT gate. To make OR, given that we already have a negated OR, all we have to do is negate it back. And to make AND, well, to say that two things are true is to say that neither one nor the other is false. So we negate the inputs. And now we have AND, OR, and NOT. It should be much easier to build the circuits that correspond to our truth table. Let's take them one at a time. How will we make the signal for A? Well, let's look at what we have. We are supposed to deliver a 1 at all times except when we have 2s being 0 and 1s being 1. So we can easily say that A is 1 when it is not the case that we have both 2s being 0 and 1s being 1. So this is a detector for the situation where we have 0, 1, and we're saying anything but that. So that will give us A. Now for B, we've got a useful shortcut. This is the truth table we've just written down. The circuit for B is exactly a NOR gate. 2s, 1s, NOR B. Now C is a bit of a tricky one. C is always true. We have been told explicitly that we're not allowed a signal that is constantly at logic 1, so we'll have to come up with a calculation that is always at logic 1. Well, the easiest way to do that is to OR something with its negation. If we have a 0 coming in here, we'll get a 1 here, and the OR gate will deliver a 1. If we have a 1 coming in here, then the OR gate will deliver a 1. So we can wire that up to either input. It doesn't matter which. Next, we have D. Well, if we look at D in the truth table, we can see that it is always exactly the same as the 2's input. So we can build this circuit very cheaply with just a piece of wire. Moving on to E, here we can see that E is always exactly the logical negation of 1's. So we can build the circuit for E with NOT. Next up, we have F, and it's a lot like A, but not quite. Again, there's only one bit pattern we want to reject. So, and that's the bit pattern 1, 0. So first of all, we build a detector for that bit pattern, a detector for 1, 0. So you write 1, 0, and then you turn the 0 into the O of a naught, and you fill in an and to insist that both are the case. And then we said that was the one pattern we didn't want, so we better put a naught in the output. That leaves us with only G, but if you're observant, you'll notice that G is exactly the same as A. We end where we begin, and we can save ourselves a bit of work just by wiring another copy of the output to G. And that's the question done.